Okay, a brief introduction to morphological image processing. Just a minute, I was trying to do something else. Let me do that. A brief introduction to morphological image processing, which is fairly recent but not very recent, maybe from the 1980s perhaps it became more popular. So when I studied image processing in 1977, this was not around at that time. There is some confusing terminology. Some of these methods and descriptions were written by most likely computer scientists using a slightly different formulation or language. And we have tried, in the next edition of the book that is coming up, we have tried to describe in terms of what we talk in electrical engineering. But some of these ideas and terminology could be a little different. And I like to call this technique morphological image processing, but some refer to it as mathematical morphology. I find that terminology confusing. We're not talking about morphology in the sense of shape, but shape is important here in terms of what is the property of the so-called structuring element. So the result is dependent upon the structuring element that is used as the filter. But the structuring element could be 3 by 3, could be a circle. In most cases it is so. So then it is just neighborhood processing. It is just how it is configured. So morphology, if we just call it mathematical morphology, I find that a little confusing and clarity is lost sometimes. So it is a branch of nonlinear image processing that concentrates on the analysis of geometrical structures in the image, in the sense there is a probing element. The image is probed with a structuring element, which could be something like this, and you go around, just like convolution. But you are looking at the image through this sort of lens that could have different shape and size, theoretically. It is based on set theory. Initially, the technique is described in terms of binary images, and then the operators can be extended to grayscale images too, and color images. So the initial formulation is based on set theory, where you only have 0 and 1. A pixel belongs to a set or does not belong. So it is probed. The given image is probed with a structuring element, and you quantify the manner, the output quantifies the manner in which the structuring element fits or does not fit within the image as it is translated. The structuring element is much smaller than the full image. Like the convolution mask, 3 by 3, even 5 by 5, 7 by 7, they're all much, much smaller than the full image. There are two properties that the operation should be increasing and translation invariant. The fundamental binary operations are related to Minkowski algebra, but let's just talk in terms of what is done here. The two basic operations are defined as erosion and dilation, and based upon this combinations of erosion and dilation, either one first or one of them first and the other second, you get two more operators called opening and closing. So these are the two fundamental operators and two secondary operators. So erosion is also known as Minkowski subtraction. If the origin lies within the structuring element, the effect is shrinking. So erosion is something is removed, erode. Protrusions smaller than the structuring element are eliminated, as you'll see in the examples. So in digital implementation, if any of the pixels within the neighborhood defined by the structuring element is off, that is 0, the output is set to 0. So if there is 1, 0, the output is 0, which means it is the minimum. So now we can talk in terms of neighborhoods. A structuring element simply defines the neighborhood. But it doesn't have to be centered like 3 by 3 on the current pixel. It could be of any shape and size. So here is some object, binary, and this is the structuring element, a circle or a disk operator. And as you run it through here, when it is sitting on the boundary, so you will have a mix of background and foreground pixels. So that much is removed in the periphery. So it is eroded, shrunk. And these holes become bigger because this is the object, the gray area is the object. That is, that much is eaten away. So holes become bigger. And small connections like this will be removed. So small connections or bridges are removed so that the objects are disconnected. But the result depends upon the shape of the structuring element. If you use a different structuring element, you get a different result. Which one you want is up to you and your application. What kinds of objects are present in your image? Round, roundish, square, squarish, rectangle, and so on. Dilation is the opposite. So instead of min, you are taking the max. So if the origin lies within the structuring element, it fills in small holes relative to the structuring element and intrusions. So instead of removing, it fills. It represents filtering on the outside and has the effect of expansion. So that is why it's called dilation or expansion. In digital implementation, if any of the pixels within the neighborhood defined by the structuring element is on or 1, the output is also set to 1. So the max of all the pixels in that region. There could be a bunch of zeros, but if there is 1, then the output is 1. So the same object using a circular disk. Now this break is connected. These holes are filled. Except this hole is bigger than this circle, so it doesn't get completely filled. This one gets completely filled. So the output depends upon the shape and size of the structuring element. And if you use a square, you get that the square is bigger than that, so this is completely filled. Both are filled, and this broken link is finished or completed. So that is dilation. Opening has the property of idempotency, that is, if you apply it again, you get the same thing. Applying once is enough. Repeated application has no effect. It is obtained by applying erosion and then dilation. So the sequence matters with the same structuring element. You don't change along the way. So if the origin lies within the structuring element, it removes objects smaller than the structuring element. So some objects are, am I moving? I don't think so. Okay. It removes objects smaller than the structuring element. It smoothens the edges of the remaining objects and disconnects objects that are connected by branches smaller than the structuring element. So this is what opening does. So this connection, you lose that much as you run the structuring element through. This is also removed. The shape of the output depends on the shape of the structuring element. So we don't have even the fan today. Okay, oh now. No AC, no fan. Okay. Hopefully it will come back soon. Closing is the two operators in reverse order. Dilate and then erode. It fills in holes and intrusions smaller than the structuring element, connects objects that are disconnected by gaps smaller than the structuring element. So everything is with reference to the structuring element, shape and size. So this is what you get with closing. So here are some examples. Binary, so this is after segmentation. The bone area has been segmented. When you erode, you get this. Dilate, you get that. Erosion has removed all these. Because there are unfilled areas here, those have been disconnected. Only the solid parts have been retained. And these objects have become smaller. If you dilate, you get that. Dilate the original. These gaps have been filled. The objects are bigger. Opening gives you this, closing gives you that. Again, it depends on what you want to do, and there are further sequences of operations that you could perform. So this is the structuring element in the scale of the whole image. It's small, that little circle. It is this big, a disk of radius pi pixels, but this image is much bigger. So that is the structuring. That little yellow disk is that disk in relation to the size of the image. Now, grayscale morphological image processing is an extension of the basic binary set-based operations. You can extend binary morphological image processing using threshold decomposition. So you could break down the grayscale image into bit planes, and you can apply it on bit planes and then recompose the image. Or you can reformulate the basic operations. Grayscale flat erosion replaces the value of an image f at a pixel xy by the infimum of the values of f over the structuring element. Dilation replaces using the supremum. Opening and closing obtains similar as in the binary case, putting the erosion dilation one after another in two different orders, so you get two different operators, dilation and now opening and closing. You get by combining erosion and dilation in two orders. There is another technique known as opening by reconstruction, which analyzes connectivity. So it is an iterative procedure to extract regions of interest from a marker or a seed. So if you have some initial result of detection of some object, you can use those as markers or seed pixels or seed regions, and then perform opening by reconstruction. It is more efficient than fuzzy connectivity, and it is useful for multi-seeded region growing. So you may get multiple pixels belonging to the same object using some detection procedure, such as calcifications. We found there are multiple calcifications and multiple seeds for a given region. You can put them through opening by reconstruction. So it says, starting with a mask I and a marker J, the grayscale reconstruction, opening by reconstruction is, for grayscale images, is defined rho I, J as the supremum of all of these iterations of dilation operators applied on J. The marker is expected to be within the object, so you keep dilating it. And then when the dilation stops, then that's the boundary of the object. You have detected the entire object. And everything else is rejected. So connectivity is brought in by the opening by reconstruction, by proper placement of the seed pixels. Now in plural, you can have multiple, or a region. So you may have multiple seeds detected, or could be there is some region of interest. The radiologist simply draws a small part of it and say, this is the core area. From here, you do region drawing. So it could be like this. 3 regions are marked. This image has so many regions. Now this is done in grayscale also, or binary, but we define in grayscale. They are just shown as white objects. They could be in grayscale. These 3 have been marked by seed regions. And at the end, we will get those 3 regions, and the other 3 that were not marked will not be selected. I'll show some examples later on. The mapping is done using fuzzy membership, using this Gaussian function. So mask is a fuzzy membership map. Marker is a seed pixel or region. So this is the seed pixel in the spinal canal, the red dot here. That is the original CT image, but everything outside has been segmented and removed. This is the fuzzy map. High membership here. Mu equal to 30, sigma equal to 17 Hounsfield-Williams in the Gaussian membership function. Mean is derived for this data set of pediatric CT images for the spinal canal, 30 Hounsfield units. And some standard deviation, we know that too. Manually mark a number of these voxels, get the mean and standard deviation for this data set, not for adults. So this will guide the membership function. And you dilate the marker within the mask until no further change is obtained between two iterations. It's an iterative process, and that is the result. So input was 1, but you can do it in 3D. I'm showing one slice. Now there are some parts, some pixels that are not connected. The values are not so high, so you need some further processing to fill that. But this is an example of opening by reconstruction where a marker, in this case a single seed pixel is obtained, is given as input. And as I mentioned earlier, with the Huff transform, that was detected by fitting a circle to the edge map. So the seed was obtained automatically. I'll show those results later on. So there is another method we have used to fit some improved or a mathematical model, let's say, a smoother contour to a detected contour. Detected meaning by some previous image processing step, we get some boundary and it could have some imperfections due to noise and variations in Hounsfield unit values. And we want to fit a smooth curve. And for that, you can make use of linear least squares estimation. There are other techniques also, nonlinear methods if you wish. But suppose you have these n coordinates, xi, yi, zi in 3D, vi. The model is given this quadratic equation. Zi prime is this quadratic relationship to xi and yi. So calculate the error between the real data z and the model z prime. You have the real data from segmentation. Z is like an improved contour using x and y. And you compare that with the real edge in the segmented image. And you say you want to optimize these values A0, A1, A2, A3, A4, A5 for the quadratic model to minimize this error. And you formulate this matrix using the data given and estimate the best set of parameters using this equation. And omega is this set of input samples, pixel values along the contour or the object boundary you have detected. So I'll show you some results of application of all of these techniques now. The CT data, we had 14 patients, pediatric cases, 40 CT exams. The ages of the patients, 2 weeks to 20 years. There was just one case, I think 1 or 2 cases. Until the age of 18 years, children are sent to the Alberta Children's Hospital. After 18, they go to the regular adult hospital known as the Foothills Hospital. But there were 1 or 2 cases, I can't remember, past the age of 18, maybe just one case, because there were patients at the Children's Hospital while being a child, or 1 or 2, I don't know, while they were under the age of 18, they continued in this data set due to follow-up. The data set, we didn't have isotropic resolution. I forgot to mention one thing. I said we can get higher and higher resolution now with CT images. HRCT is high resolution computed tomography. You can get many slices. You can get 1,000 slices with 0.1 millimeter, but that means more radiation. In pediatric cases, you have to be concerned about radiation dose. I'm not sure if these CT images, which were obtained in about the year 2000, it's a little old, 25 years, but Perhaps the resolution was limited in the CT scanners to this, or maybe there was better resolution available but at higher dose. And then with pediatric cases, considering the dose, the interslice resolution was either 2.5 millimeter or 5 millimeter, which is 10 times the intra-slice resolution, 0.35 to 0.7 millimeter. So the voxel is not isotropic resolution. They say isotropic, but it is a cube. The resolution is the same in X, Y, and Z if it is called isotropic resolution. But here the inter-slice resolution is much poorer, 10 times the pixel or voxel size compared to the intra-slice. 36 studies out of the 40 had contrast medium injection. So sometimes we encounter these difficulties, but from the header, the DICOM header, or from wherever else, you should know whether the patient had contrast or not, and various other details about the data acquisition protocol. So how do you compare the results of segmentation with a reference, the so-called gold standard or ground truth, given by, in this case, the radiologist? We assume the radiologist is God and that is perfect. That may not always be the case because, as I said, the radiologists are not in the practice of drawing boundaries of all these objects. Still, that is the reference. And you and I, we are not qualified to do that. So how do you compare? One is known as the Hausdorff distance. Now, Hausdorff distance from A to B and B to A will not be the same, so it is called the directed Hausdorff distance. H of AB, A to B, is the max over all members of A of the min of all members of B, DAB, where DAB is some distance of all the elements A to B. So you're comparing distances from A to B, but you take the min of all over all elements of B, and then you take the max of all elements over A. But then that could be switched, and then it becomes B to A. And they will not be the same in general. So if you do both A to B and B to A, you take the max of that. This is a worst case scenario. So you may have a beautiful mapping, but there could be one pixel that went away somewhere, and it will say that is your distance. So it won't average with the max there. So you're penalized for a few points that could deviate, and if everything else is perfect, it doesn't matter. So it is unfair in some sense. But this is an accepted measure. Perhaps the mean distance to closest point is a fairer measure. It says, given two sets A and B, one is your detected contour or boundary, and the other is the reference B. The distance to the closest point is defined as the min of AI minus Bj over all j. So take one point in one of the contours, AI, and find all the distances to BI, and find the minimum one, and that is the minimum. What is the closest point? I got a contour here, and on my contour I have a point. Find the distance of that to all the points along the reference contour given by the radiologist. Find the minimum one. So that is the closest point to this point. And then you average for all of the points along my contour. So what is the minimum distance between every point on my contour to every other point in the reference contour, and do average over all points on my contour. The two contours may be of different size. My contour may go like that, the radiologist may draw like this. Doesn't matter. So the two contours may have different number of points, different sizes, different shape. So find the closest point distance and then average them. It is fair in the sense, if you have a few points that are bad in segmentation, their effects will be averaged out. You may be having a good fit for 90% of the contour and 10% may be bad, and they will all be averaged. You could have volumetric accuracy, the volume of the detected region minus volume of the reference with reference to the ratio to the reference times 100%. False positive, how much are you missing? True positive, what is the intersection between the two sets? If you want false negative also, how much are you, false positive is how many extra points you're putting. False negative is how many points in the contour are you missing. True positive is the intersection between the two sets. These are treated as sets. So the pre-processing steps in our work, we have the original CT volume, grow the air region, start with the corner pixel as a reference, assume that is outside the body, it should be outside the body. The top, the patient is always on the back, so the top left will not have any material of the patient's body. There could be something, blanket or IV tubes and other things that come with the patient into the scanner. So we'll assume that is the air region, but give some standard deviations, so blankets and other things outside the body will be removed. Find the skin area, come down and get the skin boundary. We know the Hounsfield unit for skin. And then erode the skin area morphologically and take it out. Grow the peripheral fat area. Under the skin we have some fat, and depends on the patient, there could be different amounts of what is called peripheral fat under the skin. Remove that. Fat we know is negative in Hounsfield units, -10 or so. And then there is some muscle, peripheral muscle. So we know the Hounsfield units again. Grow that and remove. So you are peeling away these one step at a time from the outside. Now we call this the pre-processed CT volume. Peripheral artifacts and tissue have been removed. Now we only have the internal organs. So how do you do that? By definition, air has -1000. There could be some noise. The CT data may be represented using 10 bits or 12 bits or whatever. It could be 16 bits. So this number could change in some scanners. So the CT volume is thresholded to the range, in this case, -1200 to -400. And then 2D binary opening by reconstruction is applied on a slice-by-slice basis, using the thresholded volume as mask and the 4 corners of each slice as markers. So you need a reference point to grow the region. So the corner points are the markers. They must be outside the body. And then you give some range here. And then it is morphologically closed using a disc structuring element of radius 10 pixels, about 5 millimeters, to remove material external to the body. There could be a few other objects, blankets and so on, IV tubes and such things. The skin is the first layer from the outside of the body with a thickness in the range of 1 to 3 millimeters. The air region is morphologically dilated in 2D to include the skin. And then the skin layer could be used as a landmark for registration, segmentation. So you know that's the boundary of the patient's body. Peripheral fat is the next layer. I gave you the Hounsfield unit table earlier. Fat has mean -90. I said -10. It's -90 with reference to water. Sigma is 18 Hounsfield units. It varies in thickness from 3 to 8 millimeters in children. So voxels within a distance of 8 millimeters from the inner skin boundary are examined. If they fall within that range, minus the mean plus 2 times standard deviation, then it is classified as peripheral fat. Now there are many parameters like this that are specific to the data set. The more parameters you have, the more particular it becomes to the data set. But that should be okay. You know what you're dealing with. You don't want some general data for the entire population. You want the method to work with your data set for this scanner, for this population of pediatric cases. You must choose appropriate or select appropriate or define appropriate parameters. So we can defend the choice of these parameters, but it is good to define them and set them apart so somebody else who comes in to use it will know these have been set by the one who designed the algorithm. If you want to modify it with some reason, go ahead and do it. Then muscle. Mean is plus 44 Hounsfield units. Sigma is 14. The thickness varies from 6 to 10 millimeters, again in children. So voxels, so related to that, voxels found within 10 millimeters from the inner boundary of peripheral fat that we already dealt with, and in the range of mean plus 2 standard deviation of this type of tissue, classify them as peripheral muscle. So the peripheral fat region obtained is dilated using a disc-shaped structuring element. This is all morphological image processing of radius 2 millimeters to remove discontinuities and holes between peripheral fat and peripheral muscle. So although we said 3D, some we have done in 3D, some we do in 2D slice by slice. To do in true 3D, you should have ideally isotropic resolution. We don't have that here. So applying all of the methods in 3D may not work well because of the inter-slice dimension being 10 times the intra-slice dimension of a voxel. So here are some examples. This is the CT scan. You can see some things outside the body, blanket, and some high density object. Could be IV tube or something. So this is the peripheral artifact area. This is the region selected of the body. That is a skin layer. Remove it. The next layer is peripheral fat region. I just now described how to get that. Remove that. From this, you get the peripheral peripheral muscle area. The white area is the peripheral muscle. Initially, we defined a distance condition, but then the connectivity was imposed by opening by reconstruction and then filtered using morphological image processing. So remove this, and this is the part of the image with only the internal organs inside skin, peripheral fat, and peripheral muscle, which have been removed. So now we are ready to process this. So in 3D, this is the volume of a patient. This is after removal of peripheral artifacts. So that's the skin of the patient. The color doesn't mean anything. After removing skin layer, so this is fat. After removing fat, so this is muscle. After removing peripheral muscle, then this 3D volume has only the internal organs. So somewhere you see some ribs here, somewhere around the shoulder down to the pelvic area. That's the range of the CT scan in this case. So now we take a look at each of the internal structures we want to detect and identify and maybe remove. So ribs first, the easier ones first. High density, easy to remove, but there are some complications, not so difficult. Threshold at 200 Hounsfield units because of pediatric cases. The bone may not be as dense as in adults. So this is a fairly low threshold for bone. Morphological erosion and closing. We use the information related to the peripheral fat boundary. There won't be any bone outside. And several features of each thresholded region. We use Euclidean distances. We use compactness. We defined shape factors earlier, the normalized compactness, and length and width of each region. We will see as we go along. So the initial result of segmentation is used as a marker to perform opening by reconstruction. There are multiple pieces of voxels that are selected. Use them as markers and do opening by reconstruction, and then refine using the features defined previously, put conditions. I don't want objects or regions that have parameters outside this range. There is a central line that is defined and an elliptic region obtained adaptively inside the ribs on each slice. So we find a central line using the skin boundary and say that should pass through the vertebral column. And then we draw a circle here based upon this and say the abdominal organs should be mostly contained within that region. Not always, but these are reference regions that are marked. The rib structure was fairly easy to obtain. So here is the liver and some of the abdominal organs, the kidney and so on, the aorta, the spinal column, or the vertebral body. The column is made up of all of those. The ribs here in section. So these are the bony parts segmented. And then put that in 3D, we get that. We were not interested in perfect segmentation of the rib structure. We didn't use it for any reference, but for the general modeling purpose or to illustrate the landmarking. If you want to use the ribs as reference for something else, you could. For example, if you detect lung tumors, where are they placed with reference to ribs? That would be an important consideration. So we have the rib structure. So that's not the most difficult of the problems. Segmentation of the vertebral column in 3D. So we used the following items: the information related to the ribs and the inner boundary of the peripheral fat region. It's not necessary, but we know it is inside the body and it is on the bottom side of the image and somewhere along the central line, around the central line. So thresholding at 180 Hounsfield units, a little lower, gradient magnitude, and morphological erosion, dilation, closing. So here we have a pre-processed slice. After thresholding and removing ribs, these ribs are now gone. The central line is there. The initial result of segmentation, we get that. The binarized gradient of the detected region. Region obtained applying the combined mask, and final result of segmentation. So the sequence was shown there, and this is an illustration of those steps. So this is the vertebral body in one slice. The spinal canal is that region inside, which is what we are interested in. We're not interested in the vertebral column in this work, but if you're analyzing the image, CT image for spine deformity, and if the result is of interest in spine surgery, you will need the spinal column detected accurately, and you need the 3D representation of the vertebral column. The vertebral column, vertebral body in each slice, and then the vertebral column in 3D, or the entire spine. So detection of the vertebral column. A few results comparing manual segmentation performed by the radiologist to the result obtained by our method. So the green line is the contour obtained by our method, and red drawn by the radiologist independently. So there is good match here, not bad there. So 13 CT exams of 6 patients and 458 slices. The average MDCP was 0.73 millimeter. So not bad. That's of the order of 1 pixel in the interslice dimension. Average house top distance 3 millimeters, 3.1. So that is taking the worst case. As I said, you take the max. But this is the average. That is not bad at all. That's of the order of 1 pixel. There is a range of dimensions. It depends. If you have the 0.25, then it is 3 pixels. So in 3D, one of those examples. What is in red is the spinal canal inside the vertebral column. That is the next one. Having detected the vertebral column, next we look into that region where that circular hole where the spinal canal is, and the spine is inside that. So the CT volume, after removing all the artifacts and external material, remove peripheral muscle, detect rib structure, detect the vertebral column. This is what we have done so far. Crop the image volume containing the vertebral column. We find only that part. Compute the edge map, apply the Huff transform to detect the best fitting circle for each slice. Detect seed voxels at the center of these circles, given by the Huff transform. Calculate parameters for fuzzy region growing. Grow fuzzy spinal region in 3D. Threshold the volume and close using morphological operators and convex hull. And that gives you the spinal canal. Seed voxels, the Huff transform was used to detect the best fitting circle of the spinal canal. We saw that earlier. That method was developed by another grad student, Hanford Diglett. He had made some assumptions that we were not happy with. So later on, when Shantanu took up this project, we modified it. The radius of the circle was limited to the range, as I described earlier, 6 to 10 millimeters. The vertebral column and the rib structure were used to delimit the range. Previously, the range to search for the circle was manually defined using, not manually, it was defined using the image geometry and assuming the patient is in the middle, the spine is in the middle of the image. That may not always happen. The patient could be a little bit to the side and could be turned a bit. So here we're using the vertebral column that was detected as I showed just now, and the rib structure also we saw. The center of the detected best fitting circle with the Hounsfield unit values in the range of this mean plus 2 standard deviation, again 23 plus minus 2 times 15. Now this goes a little outside. It goes negative. So 23 minus 30. That's the range. So if you take statistics, sometimes you go out of that range. If you say I want mean plus minus 2 standard deviations, that's a little too wide. But that rule was applied to all of these steps. So this is the original image, original in the sense after removing everything outside. The cropped vertebral column area, this was obtained automatically now using the techniques shown before and using the reference of the rib structure. So the center line that we detected was using this particular body, not the image frame. This is the edge map. I don't remember if we use Sobel or Canny. For this, Sobel is enough. And the best circle detected and the center. We don't need the circle. The circle is detected only because this is circular, approximately circular in cross section. All we want is one point inside, and the center of the circle will be inside. We just want that one point, or a small neighborhood around that, and use that for region growing from every slice. So here you see that's the circle we want, but I can complete that circle. I can take this much and complete a circle. I can take that as half a circle and complete. The Huff space includes such partial circles. That's the advantage of the method and also the disadvantage here. There are so many peaks. So these are the radius values in pixels or in millimeters in the Huff space. And that is the global maximum there, marked in some sort of a teal color. Now that may not be the correct circle. We want to look in the original image what is inside that circle. So the teal circle is giving some other that if you take this and fit a circle, it looks like that. There are so many other circles. This is taken to be a part of a circle and a full circle is fitted to that. So if I take the top, how many are there? 5 circles, 6 circles. I get all of these circles in different colors. Then we ask the question, what is inside the circle in a small, not one point, but in a small neighborhood. And this circle passes the test with Hounsfield unit values in the range for the spinal canal for this data set. That has bone, this has bone. These are overlapping, but they are quite big. And we may not be interested in such big circles for the pediatric case. We know the range of the radius of the spinal canal or the diameter. Those circles are too big. So we can put limits on the size of the circle and what is contained inside in terms of Hounsfield units. By putting all those conditions, we get the correct circle, which is this red circle, and all we want is that one point and a small neighborhood around that. So the peaks detected are all these peaks, local maxima in the half space. These are the half space slices. The half space is 3D. In 2D, one slice will correspond to the image in dimensions. The other slice will have the circle radius as the parameter, c square, c of c square. So those are the local maxima detected automatically, and one of those is the circle we want. So segmentation performed using fuzzy mapping and opening by reconstruction. The detected seed boxes from a number of slices in the thoracic region were used as markers. You don't need all of them. You don't need through the entire data set. If you can't find a circle, a suitable circle, reject it. As long as you get a few points, it's enough. The mean and standard deviation calculated within the neighborhood of 21 by 21 pixels of each of these. So I said 3 by 3 could be 5 by 5. We use 21 by 21. Take the mean and standard deviation. Those are the parameters for fuzzy region growing. The result is morphologically closed to clean up the image using a tubular structuring element, now in 3D. The structuring element is in 3D a tube, or like a cylinder. Radius 2 millimeters, height 10 millimeters, and the convex hull. Use all of that information and smooth the result. So this is the spinal canal, the contour detected by our method in green, the contour drawn by the radiologist in red. There is good match here, not so good match there. So we evaluated on 3 CT exams. We didn't do this for all of them. Asking the radiologist to draw the contours of the spinal canal on 500 images was not worth the time. So he selected 21 slices and drew this for 3 different CT exams. The average MDCP is 0.6 millimeter, Hausdorff is 1.6. So some numbers, reasonable numbers. Perhaps somebody can develop a better method, but it's not bad. The spinal canal could be useful in planning radiation therapy. In image-guided radiation therapy, the image of the patient is taken into account, and the radiation beams that are applied are designed such that they intersect at the location of the tumor, around the location of the tumor, but some of them will necessarily pass through other sensitive parts of the body, including the spine. The spine should not be subjected to too much radiation. Some of the rays may pass through the spine because they have to intersect at the tumor location, but you position the rays such that a large number of the rays don't go through the spine and other areas that may be sensitive to radiation. So try to put more of the radiation onto the tumor and avoid applying too much radiation to other parts of the body. So when you know the exact anatomy of the patient and you know where these structures are, then the radiation therapy procedure could be designed appropriately to minimize radiation damage of other organs. We didn't go that far. We are just showing how to detect the spinal canal, and then you use it as a landmark for whatever application. The next is the diaphragm. The diaphragm is a large muscle directly beneath the lungs that separates the thoracic cavity from the abdominal cavity. It's a double-domed surface or double-dome muscle that separates the thorax from the abdomen directly below the lungs. So we said we will first detect the lungs, light, airy structure, negative Hounsfield units. Except fat, there is nothing else that is negative. There could be some pockets of air in the stomach and maybe elsewhere. Unlikely elsewhere, but the stomach for sure. So take the largest volume containing air and Hounsfield units less than some negative limit. And go to the bottom surface of that in 3D. Model each dome. There are two domes under the two lungs. They're continuous, but they're connected rather, but there are two separate domes of different shape. Overall shape, that is. So model each dome using linear least squares that I mentioned earlier and obtain better representation using deformable contours or snakes. So to get the diaphragm, remove all the external things as we have seen. Segment the lungs, that's fairly easy. Extract the lower surface of the lungs. Apply the linear least squares estimation procedure. Peripheral fat, peripheral muscle, ribs and the spine are all removed. And then refine the diameter using active contours. That gives you the diaphragm surface. Segmentation of the lungs, easily distinguishable from the rest of the body. The largest volume of air in the body, and iterative procedure to get the optimal threshold. The new threshold is mu b plus mu n plus 2. So we have the background and the area. So you find the optimal threshold, and you want to remove small pockets of air. I didn't mention the bowels, so in the gastrointestinal system there could be pockets of air. So here we have an example. The two parts of the lungs separated there. And this is going lower, close to the diaphragm. You may get multiple parts. We say single largest volume, but that is if you take both lungs together and all the whole area, whole volume. But when you segment in 2D, as you get closer to the diaphragm, you may get in a slice image multiple parts like this. So we get 4 parts here. So take the lower surface in 3D, put them all together in a stack, and get the lower part, the right part and the left part. And this is using the linear least squares method, the combined surface. And after applying, this is very smooth. After applying the active contour model, we get some details here. Noise is removed, but then you fit the actual edges to this contour using snakes or active contour modeling. So in 3D, this is using linear least squares and then the active contours. Those are the lungs in 3D. And these are 2 domes. From underneath it will be concave. If you rotate it from this way, it will be concave. You're seeing the upper surface, which is convex. So again, we did some comparative analysis with contours drawn by the radiologist. He did this for some of the images. In some cases, you see only one part on one side, and then two separate parts, and then one big part for the diaphragm as you go through multiple slices. The lungs, that's the heart region, spine. This is a part of one of the domes. Again, green is by our method, red is by the radiologist. That's not a good result. It went somewhere else. Sometimes the snakes can get lost. That is not bad, but some parts are missing here. Anyway, these are further modified. And this is only for separation of the abdominal and thoracic cavities. So if you lose a few voxels here and there, it should not make a big difference in subsequent analysis. So 11 CT exams of 6 patients, 109 slices. The average MDCP in 3D now is 6 millimeters. So that is of the order of the voxel size in the interslice dimension or direction. Hausdorff is a lot more. As I said, if you have one part where it is bad, Hausdorff says that is your distance instead of averaging. Let me just see, I think this is the end of the diaphragm. There is something more, we can do that later. So we got these numbers, but we need to take them, we need to consider them in the context of what we want to do next. And this was a method we proposed to get the diaphragm, and it seems to work reasonably well under these conditions. The distance measures, the Hausdorff it is used in the literature. It is a useful measure, but it penalizes you for the worst part of your result. I would rather stay with MDCP, but we are showing that. So now we can remove the thoracic cavity. So we can say everything above this dome we will throw away because we are looking at the abdominal region. We want to get tumors here, but there's still the pelvic region. We will get to that later.